close to midnight, or at least late after I left, with some issues with the quiz and with homework. So I extended that 2 days. So if you want to, if you finish it, of course, that's fine. If you took the quiz twice and you want to redo because you feel like you could do better with 2 extra days, shoot me an email and I'll reset yours so that you can do another second attempt if you feel like you want to do that. So shoot me an email and I'll open it up for you so you have I'll believe your lowest attempt and you can try again. So the main topics on the exam are all up here. I'm going to pick from the first 4 exams 3 or 4 questions. Copy, paste, edit the numbers. So the wording will be the same. So for studying purposes, for the old material, look at your exams. That's the best place to look, your exams and the answer keys that are posted. And we'll do some questions from those, of course, today. Formula sheet, if you haven't looked at it yet, it's posted on D2L, so you can look at it. You don't need to print it out, though. I'll print them out and bring them. So don't feel like you have to print it out and bring it. I mean, I guess if you've already printed it out, you can bring it. Either way. Either way. And no phones. No phones is the best. Or no Google Glass. That's no Google Glass. All right, let's go over. I guess it's up to you guys. Do we have anyone have questions from the stuff that we just did that you want to look at first? If you just start doing problems. One thing that was mentioned was the eccentricity. Let me just put that over here. And I'm not going to ask you this on the test. And eccentricity is defined to be C over A, whether you're dealing with a hyperbola or an ellipse. And there was a question in the homework and on the quiz with respect to it. It's easy to calculate C over A. And the idea is that for an ellipse, the eccentricity is going to be between 0 and 1. So E will be greater than 0 and less than 1 for an ellipse. And it's going to be greater than 1 for a hyperbola. And again, if you get it later on in math, there's some classes that may look at eccentricity in more detail. And it's a pretty simple thing. It's just sort of defining how far from, for an ellipse, the eccentricity closer to 1 means it's more oblong. And if the eccentricity is close to 0, it's more circular. And for a hyperbola, eccentricity closer to 1 means it's kind of narrow. But then as eccentricity grows and grows, the hyperbola gets wider and wider. So just sort of indicates some properties of the hyperbola or the ellipse. But in this class, it's not that important for us, so it won't be on the test. So anything from chapter 10 you want to look at? 10.3, 10.4?
I just have like a general question. When I was doing the hyperbolas and you would figure it out, the way it was like x minus 1 squared equal, and y plus 2. For some reason, when I would get that the y square thing would be different. Like it would still be the same number, but the leading sign of the plus sign would be different.
Do you have a specific one we can pull up? So yeah, it's hard for me to sort of without a specific one. I can't quite. One of the common mistakes, Kelly and I were talking about this, is that the letters switch position if you have a minus sign on the right-hand side of the equation. Is that what you're talking about? Oh. So if we have something like, we have, let's assume we have this. And let's put this, I'm going to put a coefficient here, and I'm going to put negative 16 here. So it's not in standard form yet. So maybe you've completed the square and you've ended up with that, or somehow you've ended up with this, and you know it's not in standard form because the right side's not 1. For an ellipse or hyperbola, the standard conic form would have a 1 on the right side. And how do we get a 1 on the right? We're going to divide both sides by minus 16. And that means we have to divide each of these terms by minus 16. So then the role of x and y is being reversed. And so I'm going to move the y's in front because now we have a positive. So we would have y plus 3 squared over 16 minus x plus 1 squared over 4 equals 1. And so is that kind of
that makes sense.
what you're asking about?
Yeah.
So when we go to graph this, what's our center going to be for this one? The center is going to be -1, -3. So always make sure you look at the x's for the h and the y's for the k. -1, -3. There's our center right there. And then from the center, how far up and down do we go? 4 up and 4 down. And are those points bringing us to vertices or endpoints of the conjugate axis? Vertices. This hyperbola is going to open vertically because the y's are in front of the minus sign. And so it's called the transverse axis that connects the two arches. Transverse, and the other one's called the conjugate axis. So to get to the vertices, we're going to go down 4. We're going to go up 4. So those are on the hyperbola. Those are points that are on the graph. They're not just guiding points like foci or whatever. And then to get to the endpoints of the conjugate axis, we're going horizontally how far? 2. So we'll come over here, and so we're putting points here, but technically these points are not on the graph, right? They're just guiding us. And then we'll draw a fundamental rectangle. Fundamental rectangle will be right there. Draw the diagonals. Those will be our asymptotes. All right, and then this hyperbola, like we said, the arches here, one's going to go up, one's on the graph, one's going to go down. And let's go ahead and find our foci. So to find our foci, we need to use little c. Little c squared is equal to what? Right? We add the denominators, so we do whatever the opposite of that sign is. So we're going to add the denominators and get 20 and take the square root of both sides. And that will give us 2 root 5 for c. So the foci will always be inside these arches, and that tells us how far from the center we have to go, up and down. So those foci, 2 root 5, square root of 20, somewhere between 4 and 5. So somewhere, we don't have to be very precise when we draw a graph, we just have to make sure they're inside the arches. The coordinates of the foci would then be what?
-1, -3, plus or minus 2, 5.
Exactly. Everybody follow that? The x value for the foci is the same as the x value for the center. The y value for the center is at -3, and then from -3 we're going to go down and up, whatever little c is equal to. The little c is telling us that distance. So the y value for each foci will come from that. And then the equations for our asymptotes. We look at our parenthetical expressions here. So we'll have y plus 3 equals plus or minus. And we're going to have some slope factor in there times x plus 1. To find the slope factor, we need to rise over run. We can come over here and look at our fundamental rectangle. That's a totally fine way to do it. There's the rise, there's the run. That would work. Or you can come back to your equation. You can look under the y's for the rise and under the x's for the run. Doesn't matter. Rise would be 4, run would be 2. Either place, looking at the fundamental rectangle or the equation, will generate 4 divided by 2. And 4 divided by 2 will simplify to 2.
Can you go over the asymptotes one more time?
So does this part make sense where we use the y plus 3 and the x plus 1?
Yeah.
So if we were dealing with a hyperbola that was centered at the origin, we'd be looking at equations that were y equals plus or minus some slope times x. If it was centered at the origin, those two asymptotes would go right through 0, 0. So it would be y equals a slope times x. Okay, so for us, we're replacing the y with this shift and the x with that shift. And so what we need to do, the plus or minus, of course, is because there's two, one with positive slope and one with negative slope. And then the 2 is coming from one of two places. You're looking at the slope of this diagonal line here, so you can look from the center to the corner of the fundamental rectangle, and we go up 4 and over 2. So we get 4 over 2, which is 2. Or we can look at the denominator here and the denominator here, and the rise will be 4. It's going to be the square root of 16. The run will be 2, the square root of 4. So under the y's for the rise, under the x's for the run. So we get 4 over 2 equals 2 also. That make sense? Any other hyperbola questions on that one? All right. So other review topics. So these are from the new material. Let me go back 2 slides just again. So 3 or 4 from chapter 5 and 3 or 4 from chapter 10. So exponentials and logs from chapter 5, and then the conics and the systems from chapter 10. When we're looking at chapter 5, the basic graphs and transformations. So being able to graph a basic exponential and a basic log, super important. And then being able to shift them. The stuff in 5.4, the log rules, the power rule, the quotient rule, the product rule. So being able to either expand logs or combine logs. And then equations. So 3 or 4 questions from this chapter. There absolutely has to be an equation. Probably a log equation and probably an exponential equation. So that's super important to focus on equations. And then the stuff that we just finished, 3 or 4 questions from this. So, my guidance would be make sure you can do parabolas and hyperbolas. Ellipses are the easiest of them. If you can do hyperbolas, you can definitely do ellipses. So focus on the parabola and the hyperbola first and foremost. And then there has to be a system question. The whole idea, when you get into calculus, quite frequently you're going to have to be finding boundaries of things. And to do that, you're going to need to be able to solve a nonlinear system. So I've got to have a system on there. So that's probably a really good one to practice also. So let's go ahead and do some problems. Well, this is just a collection from chapter 10 that are reasonable, so let's go ahead and do these. So this first one says find the vertex, focus, and directrix and draw the graph of this parabola. And we need to complete the square here in order to get that standard conic form for this parabola. So y squared minus 5y minus x, and then I'll put the constant on the other side. The negative 8 will go to the right. Whoops, and the x should go to the right too, actually. I was thinking I was dealing with a hyperbola or an ellipse for a moment, but I'm not. So with the parabola, the square stays on the left and everything else goes to the right. So we're going to isolate the square term. So everything that's not part of the squared variable is going to go to the right, not just the constant. If it was an ellipse or a hyperbola, the variables stay left and the constants go right. For a parabola, the square variable to the left, everything else to the right. Now we have to complete the square. So how do we complete the square with that coefficient of negative 5? What was it, 25 fourths? What did I say? Did I hear 25 fourths? 25 fourths? Mm-hmm. Yeah, everybody agree? So divide, we get negative 5 over 2. Squaring a fraction means square the numerator, square the denominator, so we get 25 fourths. If we add 25 fourths to the left, we add 25 fourths to the right to keep the balance. Keep the balance. And then this factors, this is now a perfect square trinomial. And what is going to go in here? 5 halves. So when you should hopefully observe this by now, that number right there is exactly what you did up here. Right? You took negative 5, you divided it by 2, and you got negative 5 halves. That's always the case. And then you squared it to get that. That's the relationship of A, B, and C for a perfect square trinomial. It's always the relationship. Is that B over A is equal to, B over A squared is equal to C. And then over on the right-hand side, we've got to combine our constants here. Common denominator of 4, so we're going to have x. That will be 32 fourths. So negative 32 fourths plus 25, so it's negative 7 fourths. And that tells us that our vertex, instead of a center, we have a vertex. What will our vertex be? What's h? 7 fourths, opposite of what we see. And then k, 5 halves. So that will be the vertex. Let's deal with p. What is 4p equal to? 4p is 1 here. The coefficient on the right is 1. So 4p is 1, which tells us that p is equal to 1/4. And you may or may not need to draw a picture here if it didn't ask for the graph, but if it was just asking for what the equation of the directrix and the focus were, you don't have to have a picture. If it asks you for a graph, of course you do. But even if it doesn't ask you for a graph, trying to find the directrix and focus mentally, absolutely you can do it if you're really good at visualizing. But it's always a helpful idea to draw a little sketch so that you get your orientation right. So 7 fourths, 5 halves. So that's the y value is 2.5. The x value is just under 2. So our center, vertex, right there. Approximately. And are we opening left or right?
Right.
So the p value is positive. So that tells us that we're opening right if the parabola is opening horizontally, and it's opening up if we're opening vertically. And we know since the y's are squared that it's opening horizontally, then p is positive, so it's going to open to the right. And so then we can just draw a little sketch of the parabola there. Not to be precise, but to help us think about what the coordinates of the focus will be and what the equation of the directrix will be. So the focus is then, it's an ordered pair. The focus is always on the inside of that arch, inside that parabola. So the focus is somewhere in there. And what would the x coordinate of that focus be? 2. We got that by adding 1/4 to 7/4. This focus, because p is 1/4, is 1/4 of a unit to the right of that vertex. So if you move that red dot 1/4 of a unit to the right, we add 1/4 to x. The y value, of course, has not changed if we're just moving horizontally. The y value is 5/2. And then the directrix. The directrix is right there. It is a line, first and foremost, a line, not a point. It's not an ordered pair, it's a line, so it should have an equation. And the directrix will have an equation, let's see, a vertical line, so x equals a constant. All the points on that line have the same x coordinate. We have to go 1/4 of a unit to the left of the vertex. So if the x value at the red dot at the vertex is 7/4, and we come back 1/4 of a unit, that means we're at 6/4, which reduces to 3/2. That will be the equation of our directrix. Is that good for everybody? Any piece of it problematic? I want to throw in another parabola real quick before we go on to the next one again. Let's suppose that we have something like this. Let's suppose we have x squared plus 8x equals 3y minus 2. Suppose we have that. I want to make absolutely sure that we are finding the vertex properly. So that's clearly it's a parabola because one variable is squared and the other is not. We collect the squared variable to the left, everything else to the right. We complete the square, and what are we going to add to both sides? 16. So on the left, we end up with x plus 4 squared. On the right, we have 3y plus 14. What is the vertex? Certainly minus 4 is the vertex. Vertex, that's it there. Vertex minus 4. So we have to do factoring on the right-hand side before we see the vertex. So that's the last one, there was a 1 out there, so it didn't really matter. I just want to make sure that it's clear that on the right-hand side where you're collecting the non-squared terms, you still have factoring that has to occur over there before you can see, in this case, k, the y-coordinate of the vertex. So we factor out that leading coefficient of 3, and that will give us a clear path to the vertex. Everybody okay with that? We've got a factor on the right-hand side. And a lot of them, I've seen a lot of them in the book where there's a lot of problems where the right-hand side tends to have just a 1 as the coefficient. I just want to make sure that that's obvious. And what is 4p equal to in this case? Yeah, 4p is 3, so p is going to be 3/4. And from that, we can decide which way it opens. So the X is our first, so it's going to open vertically, and then should it be up or down? Up. Find our directrix in focus. -4. 1, 2, 3, 4, and that's between 4 and 5 negatives. So 1, 2, 3, 4, 5, somewhere over here. Vertex, and it's opening up. And again, we're drawing this sketch more than anything to orient ourselves so that we can find F and D without mixing up signs and things like that. So we know that the focus is going to be somewhere inside the cup, and we know the directrix is going to be below. So the focus first. Focus will have coordinates. What's the x value for the focus? -4? Because it's on the same vertical line as the vertex, so it's got to have the same x value as the vertex. Okay, now the harder one is the y-coordinate there. And this is, we have to do a little bit of arithmetic here. I just pulled numbers out of my head, so they're not going to be as nice. So that's -14/3, and what do we have to do to the 3/4? How are we combining those? So we have -14/3, that's the y value for the vertex, then what do we do with the 3/4? Add it. So -14/3 plus 3/4, we'd have to get a common denominator, multiply that by 4, so that's 40 plus 16, so minus 56. That's 9 over 12. So that's going to be -47 over 12. And then how about the directrix? Directrix is a line, so it should have an equation. It's a horizontal line, so it should be y equals some constant. If y is a constant, which constant should it be? We're still going to be fiddling with the -14/3, right? What are we going to do with -14/3 this time? Yeah, we'll subtract. We're going to go down, so we're subtracting off 3/4. So same idea, we have to get a common denominator of 12. Multiply -4 times 4, we get -56. Multiply that by 3, we get -9. -65. Alright, so let's go back to the other slide, unless you have a question on any step there. Gone. Alright, so let's go ahead and do this one. So, a circle, which is basically an ellipse with no eccentricity. We have to complete the square of both x and y, and this one's actually not too complicated because the coefficients of both x squared and y squared are 1, so this one should be a breeze. What are we going to add to both sides for the x group? 9. What do we add to both sides for the y group? It's 1. We don't have to worry because the coefficients of x squared and y squared are both 1, so we don't have any of that extra multiplication that we have to be concerned with. So, look at that. And so this is just a nuance here. For circles, we put the radius squared on the right, but if it was an ellipse, we would divide by that and put it on the left. You could divide by 25 and you see, oh, the denominators are the same, so you're going to go up and down the same distance that you're going to go right and left, so you're going to have a circle instead of an ellipse. But knowing that it's a circle, we're going to leave the 25 on the right. And the center will be 3, -1, and the radius will be 5. So again, with an ellipse, as the ellipse becomes more and more circular, the foci get closer and closer together, and as soon as it becomes a circle, the foci overlap on the center. So this was one of those weird homework ones. I feel a little mixed about going through it because it is complicated, and I'm not going to give you one nearly this complicated. So let me just talk about it. I wouldn't write this down. The test is not going to have anything nearly this complicated. So let's see if you can follow the argument here. So we're given a telescope and it contains both a parabolic mirror and a hyperbolic mirror. So the blue one is a hyperbola, the red one is a parabola. And it tells us that they share a focus at F1, right there. So F1 is a focus for the hyperbola, the blue one, and the focus for the parabola, the red one. So they share that focus. And they tell us that it's 44 feet above the vertex of the parabola. So F1 is up there at 44 feet above. Okay. So the hyperbola's second focus is F2, which is right there, and that's 8 feet above the parabola. So what I did here was I took the 44 feet, that's from F1 all the way down to there, I subtracted off the 8, that gave 36. So that tells me that the foci for the hyperbola, we could put the other arch of the hyperbola right there. So it tells us that the distance between those two foci is 36. So that means we're going to go up and down 18 if we were to put a coordinate system right in the middle for that vertically opening hyperbola. So that's what I did on the right. I said, okay, the distance between the two foci is 36. So we're going to put our origin right there. We're going to go up 18, down 18. And they tell us that the vertex of the hyperbolic mirror is 2 feet below. Oh, not that one. Where's the other information? Oh, yeah, that's it. That's it. So we're 2 feet below that focus for the hyperbola there. So that's what we have. So F1, V1, or V is that. And the end goal is to find the equation of the hyperbola if the center is at the origin. So we just want to find the equation for this hyperbola. So we need to piece together everything that we know. That hyperbola, if it's 18 up, we know that underneath the y's we have to put in 18 squared. So that's what is going on right there. So 18 squared. Oh, did I say that wrong? 18 is to the focus, not to the vertex. It's to the focus. So it's not 18 that goes underneath the y's. If that's to the focus, that's c squared. So 18 squared is put right there. 18 squared has to equal the sum of the denominators. What's under the y's is 16 squared, because that's where the vertex is. So we're going up and down from the center 16, so under the y's, we're going to put 16 squared. To figure out what goes under the x's, we said 18 squared equals to 16 squared plus b squared. B squared is 68. Goes under there. So, a little complicated, but I know it was a homework problem. And I got at least 2 emails saying, really? Is it going to be that hard of a test? No. But in the privacy of your own home, you should be able to sit there peacefully, without anxiety, and slowly piece it together. Drawing a picture helps a ton. No anxiety. Yeah, I won't give you one nearly that hard. So let's do something that's more reasonable for the test. So, nonlinear system. We have, and as you're looking at these, it's not necessary that you graph them. It will help you if you can graph them quickly to make sure that you have the right number of solutions. But at least conceptually in your mind, you should be looking and saying, okay, that's a circle, and this is a parabola. And so maybe you're not going to graph them precisely, but at least in your mind, you know a circle and a parabola, they could meet in one place, they could meet in two places, they could meet in three places, or they could meet in four places, but no more than four. You have a circle and the parabola right through it. You could have at most four solutions. Okay, so typically with these nonlinear systems, substitution works really well. Second equation, we have y squared equals x plus 3. We're going to plop it into the first equation. X squared plus x plus 3 equals 9. So here we'll subtract everything grouped on the left, the nonlinear equation. Nonlinear equations, we put everything to one side and factor. And when we factor this, we get that x is negative 3 or 2. Those are two possibilities. And then we have to decide which equation to plug those back into. We have to do some back substitution. So we have x is equal to negative 3. We've got a back substitute. We've got x equals 2. We have a back substitute. So we have to decide which equation. And here's where nonlinear systems differ from linear systems. A linear system doesn't matter. Plug it into either equation, you're good to go. No issue. With nonlinear, you have to plug it into the equation that generates the least number of solutions. And in this case, both equations have y raised to the second power. So in this case, it actually does not matter because both equation 1 and equation 2 have y squared, so both are going to give you 2 y values for each x value. So if one of the equations had y only to the first power, you would absolutely go with that equation. And here, both are squared, so it's not going to matter. Let's go into the second equation. That looks probably a little easier. So when x is negative 3, we get y squared equals 0. So y is going to be 0. So this gives us the single solution, negative 3 times 0. Only answer for that one. Then we plug x equals 2 into the second equation. That will give us y squared is equal to 5. So y will be plus or minus the square root of 5. And then our ordered pairs. We have the 2 comma positive root 5 and 2 comma negative root 5. Get missed. So 3 answers, 3 solutions. And that fits conceptually. Okay, that's logical. So we would have 3 answers. You can imagine circle and the parabola sharing one point at the vertex and then passing through the circle 2 others. Of course you can graph it. This one's not too hard to graph. Any questions on any of the steps for that nonlinear system? Or do you have a nonlinear system that you struggle with that you want to do? Okay. We'll do some log stuff. So this type of question, most of you did pretty well with this, but this is a common one to have some errors with. So let's just go through. And the base here is just given to be b. The only way we can combine logs with the 3 log properties is if the bases are the same. They all have to be equal. So here they just call it base b. And we'll go step by step. If we want to combine into a single log, we need to get rid of coefficients first. In order to use the product or quotient rule, we need coefficients of 1. So let's get the coefficients moved up into the exponent position. So this first one is going to be log base b of x to the 1/2 power. The second one becomes log base b of y to the 2nd power. And the third one, what we typically do is leave the minus out in front and just move the numerical piece up. So we have minus log base b of x cubed. And once you have it in that form, you can combine it into one log in one step. If you wanted to do it in 2 steps, you could, but it's pretty straightforward to go to the final answer here. The 2 terms that are added together, those jump into the numerator, and they're multiplied together. And then subtracting off x cubed, that's going to throw an x cubed into the denominator. We have a like power there that we can combine. We'll end up with y squared divided by x to the 5/2. So now we've taken those 3 logs and combined them into a single log. Let's do one where we go the other way. Let's do one where we go the other way. So let's suppose that we have log base 2 of a bunch of stuff. So if we have a single log with a bunch of multiplication, division, and powers going the other direction, we want to be able to expand that. And this again, this is probably, I was going to say that you use them both in calculus, but this one in some ways is a little bit more important. We can pull stuff apart. And you can pull it apart when you get into these 2 main concepts in calculus called the derivative and the integral. You can pull stuff apart. It's easier to differentiate or to integrate little terms instead of a big complicated looking expression. So this one's probably the one that we would use more. Okay, so when we do this, we have to be aware of the order of operations and what the predominant operation is. And when we look at this, what is the predominant operation? What's the first operation that we need to split apart? The division. We need to split that division apart first. And then we can break it apart factor by factor. If that's the predominant operation, and there's division. You have all this stuff going on in the numerator, all this stuff going on in the denominator, and then you've got this division. So that's the predominant thing happening. So we're going to split it using the so-called quotient rule for logs. So it's that expression. Now when we look to the first log expression here, the predominant operation is multiplication. We have 3 factors being multiplied together. We have the 5 being multiplied by the x cubed, being multiplied by the y squared. Over here, predominant operation is the square root, is the power. 1/2 is the power there. So let's split this first one with the so-called product rule. So we're going to have log base 2 of 5 plus, we could probably do 2 steps here, I think. Log base 2 of x cubed. You pull the 3 down. So we're going to have 3 log base 2 of x. And then we have plus the log base 2 of y squared. Again, let's pull that y exponent down right away instead of waiting. And then similarly here, the exponent on the expression inside the log is 1/2. So it's going to pop in front as a minus 1/2. Log base 2 of b plus 2. So we've now taken a complicated single log expression and unraveled it to a bunch of simple logs. Simple logs, we've gotten rid of all the multiplication, division, and power on the inside. So the insides are down to a single term. Eliminate powers, products, and quotients. Any questions on any step in that process?
Where did you get the 1/2?
So the square root, that can be rewritten using a rational exponent. So the square root turns into a 1/2 power. So that's z plus 2 raised to the 1/2. And then the power rule would bring it down. So square roots turn into fractional exponents. Any other questions on it? Can you do that on Thursday? That is the ultimate question. All right, let's take a look at some equations because those are super important. So here, this may look kind of complicated, but this is actually one of the easier exponential equations. Because you can equate the exponents here, you can create bases that are the same. So here's what I'm going to do. So I'm going to try to, the obvious base to try to get everything written as, well, I guess there's multiple perspectives. I think 2 is kind of the natural way to go. You could say, hey, I can turn that into a 4 if I'm clever, and yeah, you could, but it's really a pain. I think the natural way to go is to turn all the bases into 2. So for that first factor, 4 to the x squared, I could write the 4 as 2 to the 2, and that 2 gets multiplied by the current exponent. So we have 2x squared. The second one is already good to go, second factor. And on the right-hand side, of course, we'll write it as 2 squared. And how does the left-hand side combine? What does the exponent become on the 2? What do we do with those 2 exponents? Right, so we have exponential expressions with the same base, and we're multiplying them. When you multiply 2 exponentials with the same base, you add the exponents. And on the right, we still have 2 squared. And so this is one of those classic situations. We're not, they call this, if you took log base 2 of both sides, the 2's would disappear. But what we do is equate the exponents. If the powers have the same base, the exponents have to be equal. And mathematically, if you wanted to, you could take log base 2 of both sides and get those bases to cancel. But quite simply, we just equate the exponents. So this tells us then that 2x squared plus 3x is equal to 2. Nonlinear equation, everything to the left and factor. Or a nonlinear equation. Nonlinear equation. Hopefully it factors. If it does, there's not a lot of choice. There's a bunch of primes in there. 2 is a prime. So it would have to be 2x and x, no choice there. That 2 is also a prime, so we can only have a 2 and a 1. We just have to pick the right place. So we're going to go plus 2 and minus 1, which should do it for us. Gives us 4x minus 1x for the middle term. And that tells us that our solutions are x equals 1/2 or x equals -2. And here, you can be confident that those are both solutions. It's only with the log equations that you may have introduced an extraneous one. So for exponentials, if you come down to answers, they're good. The place where you have to be wary is log equations. And that's because you have stuff like this. If you have the log of A plus the log of B, how do you combine those? Multiply. So now what if both of these were negative? If that was -2 and that was -3, then over here you have a +6. Right? And so that's not okay. So you can have these logs of negatives hidden when you use a log rule. So you have to be wary. Anytime you use a log rule, you may have somehow inadvertently introduced an extraneous answer. So if it's a log equation, we always have to check. Okay, let's try a log equation. So here, the procedure is going to be to collect the logs on one side. They have the same base. So let's collect them on the same side of the equation. So we have that. These in turn get combined using multiplication. We have that. And here's the hard part. Here's the part that I see the most mistakes. Now, the funny thing here is that you could actually make the common mistake and still get the right equation next. Okay, the next step, I should have picked something slightly different. We'll analyze what I'm talking about. Okay, so I don't need those parentheses. So here's the next step. We want to convert from the log to an exponential. So to convert, we take the inside of the log, and we set it equal to the base of the log raised to the other side. So 5, raised to the first power. The common mistake is to multiply the 5 and the 1. But multiplying the 5 and the 1 and raising the 5 to the first power is the same, so you might actually, so on the test, I'm definitely not putting a 1 on that side. Because if it was a 2, if that was a 2 right there, there's a 2, this would be 5 squared. So you get 25 and that's 10. So just be aware of that. Okay, and then we're back to old stuff. We have a nonlinear equation, so everything comes to the left of the factor. Should I think the factor previously? I think the factor is right. 5x minus 1x works. Okay, so we get two answers. Log equation, definitely have to check. So go back and look at how the equation was originally presented. It's the way the equation was originally presented that we have to go back to figure out. That's where the domain is dictated from the original presentation. But if we go up there and look, we plug in -5, that cannot be a solution because we have log base 5 with a negative number which is undefined. Even if we put -5 in over here, we get log base 5 of -1, which is undefined. So that definitely cannot be included as a solution. If we plug in 1, no problem. That creates a positive argument. Plug in 1 there, that creates a positive argument. So for a log, the argument has to be positive. What's inside has to be positive. So this tells us that our only solution is x equals 1. questions on any step there? Then let's do a harder exponential where we don't have the luxury of equating the bases. So here we are going to have to take the natural log of both sides. We have to ln it. Take an ln of the left and an ln of the right. So if you can't equate bases, take the natural log of both sides. On the left side, what can we do with that exponent of x minus 1? Bring it down front. So using the power rule for logs, exponents come in front. Common mistake here, make sure you wrap that exponent as you bring it down because the ln of 4 needs to be multiplied by both those terms. Make sure you wrap that up. On the left, we're going to do ln of 64 plus ln of 3 to the x. So that's the product rule for logarithms. We're going to separate the log of a product into the sum of two logs. Next step on the left, we'll distribute. On the right, we need to pull that exponent down. Now, is this equation linear or nonlinear? What is it? Linear or nonlinear? Linear, because the exponent on each of the x's is 1. Right? It's the power on the variable that dictates whether it's linear or nonlinear. If the power on the variable is 1 in each of the places where there's an x, it just means it's linear. And our basic rule for linear, letters left, numbers right. So different from nonlinear. Nonlinear, everything to one side and factor. Linear, numbers right, letters left. So we're going to put the two terms that have an x to the left. That. And then we're trying to solve for x. We need to isolate the x. Right now it's in two places. How do we
Factor out the x.
factor out the x? Exactly. We have x multiplied by this quantity. And over on the right, if we want to, we can combine those using the log property for, they call it the product rule. 64 times 4 is 256. The last step, we're going to divide that expression next to the x. That's multiplication. It's just a constant. So we're going to have ln of 256 divided by. If we want to, you could combine these. Again, on the test, I don't care if you do or not. You could write this natural log of 4/3. We test it. It doesn't matter. That would be our final answer. And then on the test, if you're asked to approximate, let's make sure you can type it into your calculator to get the right approximation. So if you were asked to approximate to, say, 2 decimal places, we would have to be able to type this in and get to 2 decimal places, x will be approximately equal to 19.28. So that one is an approximation. The other one is exact. Any issues there? All right, well, let's pause, take a break, 10 minutes. It's exactly 11. Perfect time. Boom. Let's go through some questions from that were either directly or at least, the numbers might be a little different, but this was an exam 1 type of question. Super common trig question. Finding the trigonometric function values given a terminal point, or a point on the terminal ray. And really kind of fundamental question. And so if we look and draw a sketch of what we're visualizing here, we're thinking about a situation like this. And the angle that is in question, we'll call it theta, we can imagine it right there. That would be the positive angle that has that terminal ray. You could use a negative angle, but as we know from trig, it doesn't matter. All angles that have the same terminal ray will have the same trigonometric function values. So for visualization purposes, that's the easiest theta to think of. The least non-negative theta is usually the one that we go with. So we have 3 quantities we need to know to find the trig values. We need x, we need y, and we need r. R is the radial distance from the origin to the point. So that distance right there. What's that? Oh, does that make sense? How do we find that r? Pythagorean theorem?
R squared, t squared, negative 3 squared.
Yeah. Now make sure you wrap up that negative 3 so that that minus will vanish. So we get that r squared is 13, so r is the square root of 13. Now we're ready to form our ratios. So our trigonometric ratios are found by looking at the 6 fractions that we've defined our trig functions to be equal to. So sine of theta. Sine, is that associated with the first coordinate or the second coordinate? Second. Sine is second, cosine is first. So sine will be negative 3 divided by square root of 13. If you wanted to rationalize, you can. You don't need to. I don't care. So there's sine. Common mistake is to forget the root 13 and just say sine of theta is negative 3. No way, though, right? We know that sine has a graph that never goes above 1 and never goes below negative 1. So sine of theta cannot be more than 1 or less than negative 1. So make sure that you put that radius in there. Square root of 13. Cosine of theta is the x value divided by the radial distance. And then tan of theta, lots of ways you can think about it. You can think of it as y over x, gives you negative 3/2. That's a great way to think of it. You can think of it as sine over cosine. You can divide this fraction by that fraction, which means multiply by the reciprocal and root 13s cancel, and you get negative 3/2. Or you can think of it as slope, slope of the terminal ray. And then our reciprocal functions are just that. We reciprocate, and we get the following. Any questions on those ratios? Do you remember those ratios? I know it's been a while. All right, this one will feel like it's really been a while. All right, graph. So graphing the trigonometric functions, we first want to factor out the leading coefficient of the angle. Leading coefficient of the angle. So in this case, I have an x over 2 there, so I'll factor a 1/2 to the front of the angle. And then what's going to go to the right of the minus? I'm going to factor a 1/2 out. What will go there? 4 pi. And you double check. You take your half, multiply it over here. Half of negative 4 pi is negative 2 pi. Double check. It's very easy to have fractional dyslexia where your denominator becomes the numerator, your numerator becomes the denominator. Really easy to want to make that just pi and divide the two out there. So just make sure you check, right? Okay, then we look for our characteristics here. So we have the following. Now, we're always going to be looking for these guys. Reflection, amplitude, period, phase shift, and vertical shift. So those are the 5 characteristics that we want to pull out of that equation, out of that function. And I generally will write them in this order because that's kind of the left to right progression as you move through the function. So the reflection is out in front, and here there is a minus, so we say, yeah, there's a reflection. And that reflection is a vertical reflection, meaning it reflects through the x-axis. How about amplitude? So you have to be super careful here. Let's put a 2. And that 2 is the amplitude for the guide function, not this original function here. That's for the guide. And I actually should probably write the guide function down before we continue, just to make that clear. So let's call it y sub g for guide. So the guide is the reciprocal function. The reciprocal of secant is cosecant. So here's our guide function. And that amplitude is for the guide. Cosecant and secant have no amplitude because they go up and down forever. They have those arches that go up and down forever. So secant itself has no amplitude, but cosine does have amplitude. So we just need to be clear that that amplitude is for the guide function, not for secant. And then the period, what would the period be? So we take 2 pi. The basic period for cosine is 2 pi. We have a period adjuster here, though, so we have a little bit more work. That's our basic period. And we have to divide that by the 1/2. So that angle coefficient here, that's our period adjuster right there. That's got to be taken into consideration. So that 1/2 is what goes right below here. So that tells us that our period will actually be 4 pi for the function f and for the guide. All right, phase shift.
Four pi.
4 pi also, right? For a different reason. That's this 4 pi. The phase shift is the opposite of what we see to the right of x. So negative 4 pi is what we see. The phase shift is opposite of that, so positive 4 pi, vertical shift, of course, 1. All right, so then we go and we have to sketch a graph. And we start with what? Which of these characteristics do we start with first?
Vertical shift?
What was that?
The vertical shift?
No. Phase shift. Phase shift is where we start first, because the whole graph is shifted. First, we're going to shift it horizontally, so we're going to go to the phase shift as our first step. So the phase shift is 4 pi. 1, 2, 3, 4. And then what's the next step? So the idea is that the phase shift is going to move the graph, and then we have to figure out what the horizontal span of the graph is. We need to know where the right endpoint of the first period is. So that phase shift is going to correspond to the left endpoint of the first period. Then we've got our graph, and then we have our right endpoint of the first period. And so if the left endpoint of the first period is right there at 4 pi, how do we get to the right endpoint of the first period? Yeah, we're going to add 4 more pi. We're going to add the phase shift. So we're going to add the period. So the phase shift takes us right here, and then we have to add the period onto that. So over here we have the phase shift plus the period. And then we go to the vertical shift. That tells us it's going up 1 unit, and so I call this the center line of the graph. So the center line, we're going to go up 1 unit, and that will be our center line right there. Up 1 unit. Center line of the graph. Then what? Only a couple of things left. Amplitude. The amplitude is going to tell us how far above and how far below the center line we need to go. So the amplitude is going to act like a floor and a ceiling for the guide function. All right, now we need to know what our shape looks like. So the function we're looking at for this guide is the cosine function. And the cosine function looks like that. So we have to combine the shape. We have to combine the shape with the reflection to get what goes on the graph. And this shape has 5 key points. There's 2 up points, a down point, and 2 mid points, or 3 center line points. So because there is a reflection, we take our basic shape, and it's going to flip. So our basic shape gets flipped. We are going to have, instead of the endpoints being up, the endpoints are going to be down on the left and down on the right. And then dead center, instead of down, we're going to be up, and we'll form this V on the center line with those 2 points. So those are the 5 guide points for the cosine function. That's going to be a dashed curve. It's a little crooked there in the middle, but that's fine. Then we throw in our asymptotes. Asymptotes are where the guide crosses the center line. Alright. Then we have to draw these arches. Arch that opens up like that. A half arch opening down, and a half arch opening down. So that will be the graph of the first period of secant with these transformations. From the graph, once we have the graph, we can kind of pick off the domain and range pretty easily. The domain. It would like to be the entire real line. But we have these pesky asymptotes that cannot be included. Lots of opportunity here for different answers. You know, the book will tend to want to look at the first non-negative asymptote. Doesn't really matter to me which one you pick. I think since we graphed it over here, totally reasonable to use that as our asymptote right there. So that's 1 pi, 2 pi, 3 pi, 4 pi, 5 pi. So x is not allowed to be 5 pi plus 2 pi k. So we go and we look for the next consecutive asymptote that's 2 pi away. The period was 4 pi, so these asymptotes are coming every 2 pi. K can be positive or negative, it's an integer, so that will take care of all the possible asymptotes. And then the range starts at negative infinity, y-axis, chugging up, and then it stops at negative 1. Negative 1, we have the beginning of a gap, and that gap lasts until we get up to 3, where the function starts again. So the range will look like that. Start with the phase shift, add the period, and go from there. Any questions on any step? All right, let's look at another one. I want to do another graph. Let's do a tangent one because that one is the one that's different. Okay, let's take a look at a tangent. So the other 5, besides tangent, we always start phase shift out of period. Tangent is different. It's the only one that's different. We're first going to start out by factoring the angle. Okay, so factoring out a negative 2, what's going to go over there?
Pi half.
Positive, negative. Negative pi halves right there. Do we agree? Negative times negative is positive. So that matches because we have a positive pi above. And then 2 over 1 times 1 over 2, those 2's cancel, so we do end up with plus pi. That's correct. Okay. First hard part. Also, first part that's really convenient. With trig functions, if you have a leading minus, you can get rid of it. You have 2 choices, depending on the parity of the function, depending on whether it's an odd or an even function. So that minus, if it's an odd function, is going to jump out to the front. If it's an even function, we just erase it. So we need to know whether tangent is odd or tangent is even. And is it odd or even? Odd. Yeah, it's an odd function, right? It looks like that. Even functions are symmetric about the y-axis. So that function is odd. The only 2 even trig functions are cosine and secant. Cosine and secant. Those are the only 2 that are even. All the rest are odd. So it's an odd function. And so that means the minus sign jumps to the front. But that minus jumping to the front finds another minus. And what do 2 minuses do together? Positive. Because it's odd, it's jumping out to the front and combining with that minus sign. Okay, properties. Same properties. Reflection, amplitude, period, phase shift, vertical shift. Is there a reflection? None. Right? There's no minus out there. Plus, no minus in front, so no reflection. Amplitude for a tangent, definitely not applicable there. Tangent goes up and down forever, so it doesn't have an amplitude. Period. Pi over 2.
Right.
So we take the basic period for tangent, and we take our period adjuster. Period adjuster is the coefficient of the angle, and that goes there. In the last graph, we did 2 pi divided by that leading coefficient. But for tangent, the basic period is pi. It's narrower than sine or cosine. So the basic period is pi. And we take the basic period divided by the leading coefficient. Phase shift here. Opposite of what we see. Pi over 2. Vertical shift down pi. Okay. In the last one, and in all the other 5, we start with the phase shift and then add the period. Slightly different here. We do start with the phase shift, and then we do go to the period, but we do it differently. Okay, so the period is pi over 2. So let's suppose that this is pi over 2 right there. What do we do with the period? We split it in half. Exactly. We take the period, pi over 2, we're going to split it in half, and we're going to use the phase shift as the midpoint of the period. So the 2 points we're going to be using are here and here. So the period is pi over 2, and that's what this distance is, right? From there to there, that would be pi over 2. We're going to label, this would be pi over 4, and this would be 3 pi over 4. So we're taking the period, and we're positioning it so that the phase shift is in the midpoint of the period. So with the other problem, we added the period to the phase shift, and we'd be out here. And now, what's nice about the tangent is as soon as you do that, that provides your asymptotes. So your asymptotes are going to be on those edges. Okay, vertical shift, that's next. So we're going down 5 units. 1, 2, 3, 4, 5. And that tells us that our center line is going to be right across there. We have no amplitude to deal with. We have a shape we've got to deal with. Tangent goes up to the right. That's our shape. There's only one key point that we generally use for tangent. That's right there. So that one key point is right there. So now we have to combine our shape and our reflection to put the curve in here. There is no reflection, so the shape should match. If there was a reflection, the shape would change. We've got this as our graph. That's the first period of the transformed tangent. Domain of that? Green. Okay. Domain, it wants to be all reals, but there's these pesky asymptotes. X cannot be an asymptote, so x cannot be equal to pi over 4. Yep, exactly. Pi over 4 plus pi over 2k. So that pi over 2k, that's the distance between consecutive asymptotes. And for a tan or a cotan, that also matches exactly the period. Because one period of tangent or cotangent is in between 2 consecutive asymptotes. So for tan or cotan, the period is the distance between consecutive asymptotes. But for sine or cosine as guide functions, for secant or cosecant, the distance between consecutive asymptotes is always half the period, 2 pi. And then how about the range? All reals. There's no gaps as we go vertically. No missing y values. So there's tangent. Okay, well, let's go to something new next. Let's say new, it's not new. So double angles. We cannot just double values here. We can't just factor out the two. It's a little more complicated. We know from our identities that sine of 2 theta is 2 sine theta cosine theta. We know from our identities that cosine of 2 theta is cosine squared theta minus sine squared theta. And tangent of 2 theta, we usually write it as sine over cosine. Instead of remembering or dealing with another identity, just do that. So this tells us to figure out sine and cosine of 2 theta, we need sine and cosine of 1 theta. So both of these expressions depend on knowing sine of 1 theta and cosine of 1 theta. Cosine of 1 theta, sine 1 theta. So somehow we have to use the information given to figure out sine and cosine of 1 theta. Sine and cosine of theta. So let's go look at a little sketch. We're told that theta is in quadrant 4. So I'm going to draw a terminal ray in quadrant 4. And it says the slope is negative 4. Tan theta equals negative 4 means that the rise over run is negative 4. So we've got that sketch. And what we want to do is pick an ordered pair that satisfies the condition. There's one ordered pair that's kind of the most natural to pick. If we want the slope to be negative 4, we want y over x to be negative 4. X in quadrant 4 has to be positive, y has to be negative. The natural choice would be negative 4 for y and 1 for x. Then you have y divided by x is negative 4. That's what we need here. We need y over x equal to negative 4. We then have to calculate our radial distance. So we know that r squared is 1 plus 16. So r will be the positive square root of 17. Now that we have x, y, and r, we can calculate sine, cosine, we can calculate any of the 6 trig functions. In particular, when we come over here, we know that cosine of theta is 1 over root 17, and sine of theta is minus 4 over square root 17. So once we have x, y, and r, calculate our ratios for sine and cosine, and then we're flying. So here we have 2 times sine of theta is negative 4 over the square root of 17 times cosine of theta, which is 1 over the square root of 17. Square root of 17 times square root of 17 is 17. So we have minus 8/17. That's our value. All right. Next one, we do cosine squared minus sine squared. Cosine squared is 1/17. Sine squared is 16/17. We end up with minus 15/17. In the last one, we do negative 8/17 multiplied by negative 17/15. So we end up with a positive 8/15. All right, divided by cosine. quadrant, does 2 theta have to be in? Which one? 3. Sine and cosine are both negative, and tangent is positive. Quadrant 3. Marvelous. I'll do a few compositions. So one thing that we have to remember, let's put this at the bottom of the page. So with inverse trig functions are angles. That was kind of the first thing that we talked about with inverse trig functions. Inverse trig functions are angles. And we need to remember where they live, where in the unit circle they live. So if we imagine inverse cosine of some number, inverse sine of some number, inverse tangent, we just look at the 3 parameters. Which side, or which part, which half of the unit circle does inverse cosine live on?
Huh?
What did somebody say top half? So inverse cosine, top half. How about inverse sine and inverse tangent? Both of those are on the right side. So this tells us that we interpret the picture. Inverse cosine is an angle that is greater than or equal to 0 and less than or equal to pi. That's what that picture tells us. But inverse cosine is an angle on top. That means it could be anywhere between 0 and pi. This tells us that inverse sine is an angle that's between negative pi over 2 and pi over 2. Some angle on the right side. Similarly for inverse tangent, the only difference is that we don't include the endpoints. So we use strict inequalities instead of compound inequalities. Okay, so those are the 3 main things for our inverse trigs. They're angles that are restricted to the top or the right half of the unit circle. Okay, so when we look at this first one up here, the most common mistake is to just, of course, the most common mistake is to just erase that and write 7 pi over 6. What quadrant is 7 pi over 6 in? Down in quadrant 3. We're dealing with an inverse sine. Can inverse sine be an angle in quadrant 3?
No.
So that doesn't work. We cannot simply undo those functions there, because 7 pi over 6 is not in the range of inverse sine. So if that's the case, just do it, one step at a time. Let's calculate the sine of 7 pi over 6. 7 pi over 6 is on the 12-sector circle. And we know that 7 pi over 6 is down in quadrant 3 right there. And that point has coordinates negative 3 or negative root 3 over 2, comma negative 1/2. So what is the sine of that angle, 7 pi over 6? Negative half. Sine is always the second coordinate, the y coordinate, so sine is negative 1/2. So we're just going to plot that in here, just working our way out. Now we can answer this question. So it says it's the angle on the right side of the circle with a sine value of negative 1/2. That we know that we're on the 12-sector circle. So we have to just figure out which place we're at here. Let's see. So that one, that's the one, right? That's where the y value is negative 1/2. So our answer is this angle right here. We cannot go outside of the right-hand side of the circle. So what is our final answer then? Negative pi over 6. That's our final answer. questions on that? That good?
Let's just move this over here.
We need space for this next one. Okay, that one, the next one, we have a variable instead of a numerical fraction in there. And we are dealing with an inverse sine function. Let's draw a sketch. We know that inverse sine is an angle on the right half of the circle. So we have inverse sine of this variable fraction. So what we need to do is set up a sketch that satisfies this angle condition. Inverse sine is an angle on the right. We can pick quadrant 1 or quadrant 4. It doesn't matter. It'll all come out in the wash. So I'm going to just pick quadrant 1. And that angle right there, I need that angle, let's just call it alpha. Inverse sine is an angle, alpha. So I need that angle to satisfy the condition that sine of alpha is t over t minus 1. So I just need to position some stuff in here. So sine is the second coordinate. So I need this second coordinate divided by the radius to be that. So the easiest choice is to make the radius t minus 1 and the y coordinate t. That will be the angle on the right side with a sine value of t divided by t minus 1. And then we have our unknown. We have this x. We don't know what that is in terms of t. But we have a Pythagorean identity we can use. We know that x squared plus t squared has to be t minus 1 squared. That enables us to solve for x. So that tells us that x squared is equal to, let's FOIL this out, we get t squared minus 2t plus 1. Subtract t squared from the left side. So we get x is equal to positive or negative square root of 1 minus 2t. Or negative 2t plus 1. Either way. And what do we pick? Positive or negative? Yeah, we'll pick the positive because we're on the right side of the unit circle. And on the right side, x values are positive. So we're choosing this. And that should make it clear why it didn't matter that I picked quadrant 1 for this terminal ray. If I picked quadrant 4 for the terminal ray, I'd still be picking the same x, the positive x, regardless of where I selected that angle to be. Now we're really close to being done. So secant of alpha, we've got a picture of alpha. We just need to know how to form the secant ratio. Secant is the radius, t minus 1, divided by x or y. Secant is r over x. Cosine is x over r. Secant is r over x. So there's r, and then x we already found. Oh, that's 1 minus 2t. So that would be our final answer. Any step there that you need help with? You're not sure about? Definitely some steps there. A bunch of steps. Do you want to do another one of those, or you do one more of those, or do you feel like you have enough? All right, good takers. Keep on track. Keep on track. Okay, find all radiant solutions for this triple angle equation. So that's not just theta, so it's a triple angle. So it's a multiple angle equation. That's what the book would refer to that as. And what we always do when we're solving equations, we're going to have to go to a unit circle and try to get a sense of where these solutions live. Sine of 3 theta is root 3 over 2. The root 3 over 2 says 12 sector unit circle. Root 3 over 2. Who is a 1/2? A 1/2 or a root 3 over 2, 12 sector. I think it's root 2 over 2, 8 sector. So sine of 3 theta is positive root 3 over 2. So we need to figure out where on that unit circle we're looking at. And sine is the second coordinate. So these are the two places where sine is equal to root 3 over 2. And sine being the second coordinate. So we have a couple of options here. So this tells us that 3 theta is either equal to pi over 3 plus 2 pi k, or 3 theta is equal to 1, 2, 3, 4 pi over 6, which is 2 pi over 3. So those are our two options. 2 pi over 3 plus 2 pi over 3. Now I got it right. I have a little more. So those are our two choices. Pi over 3 plus 2 pi k or 2 pi over 3 plus 2 pi k. Our goal is to find theta, not 3 theta. So what do we do to isolate theta? Divide by 3. When you divide, you have to make sure you distribute. We're going to get pi over 9 plus 2 pi over 3 k, or theta is equal to 2 pi over 9 plus 2 pi over 3. Okay. So this is what we would categorize as all solutions. All solutions right there. Now, they say, find the particular solutions that fall in the interval 0 to 2 pi. All right. So, when we look at these, certainly pi over 9 is between 0 and 2 pi. Then we start adding 2 pi over 3 repeatedly. And if we want, it might be helpful if we write 2 pi over 3 with a denominator of 9. So that would be 6 pi over 9. That'll help us add. So 6 pi over 9 plus pi over 9 is 7 pi over 9. Then add 6 pi over 9 again, so we get 13 pi over 9. And if we were to be sort of mindless and keep on adding, what we would notice on that fourth one is that, oops, we're greater than 2 pi. Right? 18 over 9 is 2. We went more than that. So that's not one of our solutions. That's more than 2 pi. So here's where we notice the following. We have a triple angle equation. When we look to our first solution there, that first solution is generating 3 answers. And so we see 2 answers. But if we take the 3 and multiply it, we're going to get a total of 6 answers. 3 for each of those representative solutions up there. So when we get the other ones, we come over here, we get 2 pi over 9. Add 6 pi over 9, so we get 6 plus 2 is 8 pi over 9. Add 6 to that, we get 14 pi over 9. And if we were to add 6 to that, we get 20 pi over 9, which is again more than 2 pi. So those are our 6 particular answers. If we're looking into the interval 0 to 2 pi. Good? The cobwebs falling away, hopefully. Turning into slime. Roots. Roots. Okay, so here we have problem. We want to find the third roots of a number. Not the third power of a number, the third roots. Two totally different questions. Right? You could have a complex number and you could find the third power, which means multiply it by itself 3 times. Or you could find the third roots. The third roots means finding 3 numbers that have a third power equal to the number in question. Okay, so we're trying to find roots. So generally my suggestion is to write an equation that will have the solutions equal to the roots that we're looking for. So that's the equation. We're trying to find the third roots of that complex number. Next step is to rewrite that complex number in trigonometric form. And that complex number, we are suspecting that it might be a multiple of a complex number that's coming off of a 12-sector circle. Because of that root 3, I'm thinking, oh, hopefully it's a multiple of a 12-sector unit circle number. That's in quadrant 2, negative and positive. We're going to come down to quadrant, we're going to come to quadrant 2. The root 3 is in the first position, so x. So I'm thinking, all right, let's take a look at this complex number in quadrant 2 on the complex unit circle. That number is minus root 3 over 2 plus 1/2 I. That's that number. And is there a scalar that I can multiply that number by to get this? 16. So if we take 16 and multiply it by negative root 3 over 2 plus 1/2 I, boom, we get that. This allows us to say that the right-hand side is 16. What is the angle there? 5 pi over 6? 5 pi over 6, so we can write this as cosine of 5 pi over 6 plus I sine of 5 pi over 6. Or you can use the shorthand notation, which I think is a lot easier. We write that as 16 CIS 5 pi over 6. Either way. Now, there's 3 answers. The first answer we're going to call Z sub 1. Second answer, Z sub 2. Third answer, Z sub 3. And the way we're going to find that first answer is to write the right-hand side raised to the 1/3 exponent, and then we're going to apply de Moivre's theorem. De Moivre's theorem says that we take that 16 out in front and raise it to the 3rd power, and what do we do with the 1/3 in the angle? Multiply it. So 5 pi over 18. That will be our first answer in trigonometric form. And at this point, I should identify that we have 3 solutions. How far apart? So we take 2 pi and divide by 3. So if we wrote it in radians, it would be 2 pi over 3 radians apart. Typically, when I was doing these in class, I was using degrees for these types of problems just because it helps to clarify a little bit, but it doesn't really matter with these degrees or radians. So 2 pi over 3, which is 120 degrees apart. We're good in degrees. Okay, so there's our first answer. So our second answer then, all we do is leave the radius out here alone, CIS. We have to add that to this. And what if we got a common denominator of 18? That would be 12 pi over 18. So we have to add 12 pi here, so we get 17 pi over 18. And then our last answer, 16 to the 1/3, still the radius of the circle where the solutions are. And we have to add one more. So the CIS, we add, let's say 12, 12, so 12 plus 17 is 29. So those are our three answers in trig form. I will definitely then ask you to round them. Let's make sure we can do that. Okay, so we have them in trigonometric form. Now we have to be able to type them into our calculator, so make sure you're in radian mode because that angle is given to us in radians. So then we would do 16 raised to the 1/3 power. Make sure you wrap that exponent up. Multiply by cosine of 5 pi over 18. 5 pi divided by 18. Wrap that angle. We should be at a 1.62 if we go to two decimal places. And then, sine of 5 pi divided by 18 is 1.93 times I. There's your first one. Second one, same idea. Second one, we have 16 to the 1/3. The only thing we're changing is the angle is 17 pi over 18. So we get plus 0.44i in the first part. Change signs of cosine. It will be negative 2.18. 3. We have to change 17 to 29. Negative 2.375. All right, so here are the answers rounded to two decimal places. So those three numbers, when cubed, will give us the original number up there. So these three numbers will have a third power equal to the original number. All right, any questions on the roots problem? Go to exam 4. So here, division algorithm, we want to rewrite the polynomial as dq plus r. So we're going to use synthetic division, put a -2 in the corner. Bless you. And then we have 2, -1, 0, 3, -6. What's 17 times 2? 34? Starting to get tired. Okay, so this tells us then that we can rewrite p as x plus 2. Make sure you get your signs situated here. This corner number is always the 0 of the corresponding factor. So then we've got our cube. That started as a fourth, so it should be 2x cubed. Minus 5x squared plus 10x minus 17 plus the remainder. And then what is p of -2? 28. So on the test, make sure If it says what is p of negative 2, don't just do this and put a box around it with no indication. Make sure it's clear to me that p of negative 2 is 28. I want to lose silly points. That was a pretty straightforward one. Okay, let's do a harder one. So let's graph this rational function. We've got a rational function here, and I'm going to factor it. So there's our rational function. Vertical asymptotes. That comes first. X equals what? No. 3. And why is negative 3 not an asymptote? Because it's a hole, right? It's a simultaneous 0 for top and bottom. So that means that there's a hole at negative 3 comma something. How do we figure out the comma something? Yeah, we plug it in. We can cross out the common factor. We're going to plug in the negative 3 here. So we're going to get negative 5 over negative 6. So 5 over 6. All right. Horizontal asymptote or oblique asymptote. Which is it? The powers match. If the powers match, then it's going to be horizontal. And we're going to look at the quotient of leading coefficients. So that horizontal asymptote will be y equals to 1. Now, it is possible for horizontal asymptotes to be crossed. Let's check to see if it's crossed. We can go to the original function or the reduced function. It doesn't really matter. I'm going to go to the original right here just because I have it right in front of me. Doesn't matter. Multiply both sides by x squared minus 9. Those cancel. We end up with x equals, we add that, negative 3. So that horizontal asymptote is crossed at negative 3. What? 1 x squared minus 9. Y x equals negative 3. Does that make sense? Let's keep going for now. We're in a minute left, so let's keep going. Horizontal asymptote. Oh, no. Here's what the problem is. So when we, no, I can't do that. We have to set this 1 equal to the reduced function, not the original function. If we want to see whether that horizontal asymptote is crossed, we need to go to the reduced function. X minus 2 over x minus 3. That's what we have to do. So here we get x minus 3 equals x minus 2. The x's cancel. We get negative 3 equals negative 2. No solution. So that means it's not crossed. So you have to go to the reduced function if we want to know whether the asymptote is crossed, not the original. That. Okay, x-intercepts or intercept. We look to the numerator for the 0 that's not the whole. So 2 comma 0, x-intercept. How about the y-intercept? 0 comma, here it doesn't matter with the y-intercept. We get 0 comma 2/3 in either place. So that's our y-intercept. And then I'll just sketch the graph. So vertical asymptote at 3. There. 1, 2, 3. Horizontal asymptote at 1. There. X-intercept 2 comma 0. Y-intercept 0 comma positive 2/3. That's about right there. Whole is negative 3. 1, 2, 3. Comma 5 over 6. That's just above 1. So it's up here somewhere. Something fishy is definitely happening.
Isn't that just under 1?
Oh, that's what it is. Thank you. Just that didn't work. Okay, wait a minute. Fishy is not. All right, then we connect the dots. So we have an arrow going out. It's going to go through this, going down. And then over to the right, it has to be up there because there's no eccentricity there. Thank you. 5/6 is less than 1. Thank you. All right, we'll stop there. And test on Thursday. Jessica's going to be around like 12 hours tomorrow. Oh, wait, no.
I'll be here Thursday morning.
Thursday morning. Why not?